All right, let's talk about radio. Specifically, let's get into the secret language behind it. We're going to dive deep into frequency modulation, FM, and figure out the science that makes your favorite songs sound so incredibly good.
You know exactly what I'm talking about, right? You're in your car, you flip over to an AM station, and it's just a mess of static. But then you hit that FM button, and boom, it's crystal clear. So what's the deal? Why is there such a huge difference? Well, it all comes down to this really clever trick and how the sound gets packed into the radio wave.
Okay, so here's the big secret. AM radio, or amplitude modulation, encodes sound by messing with the power of the wave, making it taller or shorter. The problem? Things like lightning and electrical noise also mess with the power, so your radio can't tell the difference between the music and the static. But FM is way smarter. It keeps the power totally constant and instead changes the speed, or the frequency of the wave. And that one little change, well, it makes all the difference in the world. So to really get to the bottom of this, we're going to go on a little 5-step journey. First, we'll cover the basics. What even is frequency modulation? Then we'll check out the signal's unique fingerprint. After that, we'll look at the two very different personalities of FM, tackle the big bandwidth question, and finally, we'll see how your radio magically decodes it all back into sound. Okay, part 1. Let's start at the very beginning. To really wrap our heads around FM, let's just imagine we want to send one single, pure sound through the air. Like one perfect note from a flute.
Now, this definition looks pretty academic, right? But trust me, the idea is super simple. Just picture a steady, humming radio wave. We'll call that the carrier. Now take your message, say a piece of music. In FM, the loudness of that music tells the carrier wave how fast to oscillate or wiggle. A really loud part of the song makes it wiggle super fast, and a quiet part makes it slow right down. That's it. That's the core idea.
So let's stick with that flute note for a second. That one pure note is our message signal. The loudness of that note directly controls how much the carrier wave's frequency changes. See? The information is now encoded in the speed of the wave, not its strength or power. This is the key. Okay, now we're getting to a really, really important concept. It's called the modulation index, often shown as the Greek letter beta. All it is, it's just a number, but it's a super important number that tells us how much the frequency is actually changing. Think of it as the secret ingredient, the one knob that controls literally everything about the FM signal that follows, how much space it takes up, what it's good for, everything. All right, part 2. We've encoded our flute note into a radio wave. So, what does this thing actually look like now? If we were to put it under a sort of frequency microscope and see all its different components at once, we'd see its spectrum. And let me tell you, it has a very unique fingerprint. Whoa, okay. I know what you're thinking. That looks intense. This is the math behind FM, using something called Bessel functions. But look, don't let your eyes glaze over. You absolutely do not need to solve this equation. What matters, what's really cool, is what this math tells us about the signal's structure. So what that crazy math actually means is this. The FM process creates the main carrier signal right in the middle, but it also creates a whole bunch of other signals on either side, called sidebands. And here's the wild part. It theoretically creates an infinite number of them. Unlike AM, which just gives you 2, FM creates a ton. And guess what determines how much power goes into each of those sidebands? Yep, it's our old friend, the modulation index, beta. And this is where things get really practical. Because based on the value we choose for that modulation index, we end up with 2 totally different flavors of FM. You could almost think of it as FM having 2 distinct personalities, each good for a different job. Let's break it down. First, you've got Narrowband FM, or NBFM. Here, the modulation index is kept really, really small. The result? A signal that doesn't take up much space at all. It's super efficient, which is why it's perfect for things like walkie-talkies and police radios, where you just need to get clear voice across. But then, you have Wideband FM, WBFM. For this, you crank that modulation index way up. This creates a whole bunch of powerful sidebands and, yeah, it uses a lot more space on the airwaves. But the payoff? That's where you get that amazing, high-fidelity, rich audio quality that you expect from your favorite music station. Okay, so this leads us to a pretty big, kind of obvious question. If an FM signal technically has an infinite number of sidebands, how in the world do we broadcast it? Radio channels have very strict, finite limits. It sounds impossible, right? Like trying to park an infinitely long car in a normal parking spot. This right here, This is the core engineering challenge of FM. You have this beautiful signal that goes on forever in theory, but you have to stuff it into a tidy, well-defined channel. So how did the engineers solve this puzzle? What's the trick?
Well, the answer is a wonderfully practical rule of thumb called Carson's rule. The brilliant insight here is that, yeah, the sidebands go on forever, but their power drops off really fast. Most of the energy is packed close to the center. So Carson's rule gives us a simple formula to figure out a bandwidth captures about 98% of the signal's total power. We just ignore the tiny bits way out on the edges. And by doing that, we get almost all of the quality without needing an infinite channel. It's a genius compromise. This road analogy is perfect for understanding this. Think about it. Narrowband FM is like a narrow country road. It's efficient, it doesn't take up much space, but one bit of traffic or noise can cause a total jam. Now, wideband FM, that's like a giant 8-lane superhighway. Sure, it takes up a massive amount of real estate, but your signal can just cruise along completely unaffected by any noise on the shoulder. And that right there is the fundamental trade-off of FM. You are literally trading real estate on the airwaves for a clear, smooth, high-quality signal. All right, we're on the home stretch. We've created the signal, we've figured out how to transmit it, but what about the other end? How does your radio actually catch this complex wave and pull that original flute note back out of it? This last magic trick is called demodulation. So one of the older ways to do this was with something called a frequency discriminator, and it's actually a pretty clever hack. The circuit does it in 2 steps. First, it has a special component that converts the changes in frequency, the speed, back into changes in amplitude, the power. So it essentially turns the FM signal back into something that looks a lot like an AM signal. And from there, step 2 is easy. You just use a standard detector to pull the message right out of those power variations. But today, we've got something way, way better. It's called a phase-locked loop, or a PLL, and it is such an elegant solution. Basically, the circuit has its own little internal oscillator, a pacer, that tries to perfectly lock onto and track the frequency of the incoming FM signal. And here is the absolute magic of it. The control voltage it needs to keep that lock, to stay perfectly in sync. That voltage signal is a perfect replica of the original audio message. It is just so precise, and it's phenomenal at ignoring noise. And I want to be clear, this isn't some obscure piece of lab equipment. We're talking about the radio that's in your phone right now, or the one in your car's dashboard. Every single modern FM receiver uses a PLL to demodulate the signal. It's the tiny, brilliant engine that turns those invisible radio waves back into the music you're listening to. It truly is the gold standard. So let's just step back and put it all together. This is it. This is why FM completely won the quality war for music broadcasting. Its noise immunity is excellent because it just ignores changes in amplitude. Its audio quality can be amazing because it uses that wider bandwidth. And it's even more power efficient. It made one simple, brilliant trade. It used a bigger highway on the radio spectrum in exchange for a perfectly smooth, clear, static-free ride for the listener. And that kind of leaves us with a final thought, doesn't it? The whole story of FM is about this one fundamental trade-off: more bandwidths for better quality. So as we move into our modern world of digital streaming and podcasts, it's worth asking, what are the new trade-offs? Are we trading pristine audio quality for the convenience of a tiny file size? Or maybe we're trading our own data and privacy for a perfectly curated playlist. The technology is always changing, but that